Okay, so we just did tutorial 2. We did a bifurcation analysis on a system which exhibits hopped bifurcations. So with that, we will complete this. We will finish the bifurcation analysis, and we have to move on onto chaos. So what is chaos? From Hiroki Sayama points out several observations about chaotic systems. So a chaotic system is chaotic behavior is a long-term behavior of a nonlinear dynamical system that never falls into any static or periodic trajectories. It looks like random fluctuations, but still occurs in completely deterministic simple dynamical systems. It exhibits sensitivity to initial conditions. Colloquially, this is known butterfly effect. Occurs when the period of the trajectory of the system state diverges to infinity. This point is actually related to something called period doubling cascades. No periodic trajectories are stable. So we will, in the next part of the lecture, we will simulate a certain chaotic system, and we try to note these points as we observe the chaotic trajectories. This is completely not a formal definition, but just an intuitive observations. We will not really go into formal mathematics of chaos in this course. Chaos is not some kind of artifact of computer simulations. It's actually a real phenomena, and it occurs quite frequently in nature. So it's prevalent phenomena that can be found everywhere in nature, as well as in social and engineered environments. So, for instance, a lot of oscillators, natural oscillators, can get into chaotic modes of behavior. So, for instance, a heart arrhythmia is a chaotic dynamics of a normally deterministic system. Things like you can construct simple dynamical systems, for instance, coupled oscillators, which enter this kind of unpredictable but deterministic dynamics. Also, many electric circuits exhibit chaotic behavior, and so on. There are lots of systems. We'll start start with discrete dynamical systems, and then we'll look a little bit at continuous dynamical systems, which exhibit chaos. So recall the logistic map from last week. So we recall this map sometimes is used to model population dynamics. If it's a discrete map like this, then it actually exhibits a chaotic transition at certain it exhibits chaotic behavior at certain values of R. So let's have a look how the dynamics looks like for several different values of R. So if you set R to equals 2.8 and you do simulations and then plot the time series, this is what you get. So you start with, let's say, 0.1, and then you go up, and then you have a brief oscillation, and then your system settles into a steady state. It's on a fixed point. You can also represent this in a cobweb plot. So remember, the cobweb plot works like this. So you have the line, so on the x-axis you have xn, and then the y-axis you have xn plus 1. This is just a straight line, so xn equals to xn plus 1. This is our function rxn 1 minus xn, and then you just follow the dynamics. So you start at xn x0 equals to 0.1, then this is going to be your xn plus 1, then this is your so this is your x1, this is your x1, x2, and so on. So you're basically going to do this kind of construction until you follow this construction until you settle into your equilibrium point, which is here. So now let's change R a bit. If you set R to 3.3, you get your system does not settle into a constant value. It actually oscillates between the two values. So they're basically two circles here, two squares here. So this is actually there was a bifurcation here, a bifurcation from period 1 oscillation. So period 1 means that you keep repeating, the system repeats itself in one step, to period 2 oscillation. So here the system repeats every 2 steps. So this is a bifurcation. Now if you increase R further, you get to a period 3. So system repeats itself every it's period 4. Period 4 system repeats every 4 steps. So it's the period doubled again. So this type of bifurcation is called period doubling bifurcation. And then you increase it further, and suddenly your system does not repeat itself anymore. So it's this is a chaotic regime. So now the system is exhibiting chaos. Okay. You can represent this kind of bifurcations on, or it's called a bifurcation diagram. So this bifurcation diagram is slightly different to the one that we had before, and it's used for discrete systems. So here you vary R. So I'm not sure this is a logistic map, but the point is the same. So you vary R, and then you represent the location where your system is located, where it spans. So if you have if your state equilibrium point is of period 1, so you have your system spans at only one, it's located at one particular point. Then you have one period doubling bifurcation. System spans it can take 2 values. Then you approach another period doubling bifurcation. Then your system can be in 4 places, right? So this kind of thing is called the period doubling cascade, and it's often a precursor to chaotic behavior. So there are lots of period doubling cascades, and then you enter a chaotic regime where your system can be located in many number of places, and it does not repeat itself anymore. And if you go further, you see that there are some stable regions again. So and with their own little period doubling cascades here. So this is a very often a signature of chaotic systems. The period. Notice the fractal structure. So this the tree-like structure. So a lot of chaotic systems display fractal behavior. Right. Okay. So this is one way of finding chaotic behavior in discrete dynamical system, is to generate such plots, such bifurcation diagram. Okay. Another signature of a kind of measure of chaos is so-called Lyapunov exponent. So Lyapunov exponent measures how quickly an infinitesimally small distance between two initially close states grows over time. So formally it could write it like this, the Lyapunov exponent lambda. So if your lambda is greater than 0, then the distance between the trajectory grows exponentially, and this often indicates a chaotic trajectory. A practical way of computing lambda is to use this formula. So if you go to Hiroki Sayama book chapter 9, they show how to get from here to this formula. So this formula is nice. You can just essentially you compute the dynamics of your system, and then you evaluate this quantity log df by dx, the absolute value of log df by dx, and then you average over the simulation. Right, so the average is captured by this 1 over t. Right. Okay. So if you're let's check if this actually works. So if I take my logistic map from before, I computed my bifurcation diagram, so this is how it looks, and then I computed my Lyapunov exponent. So well, when Lyapunov exponent is 0, it indicates our bifurcation points. So the Lyapunov exponent is actually like it's like a generalization of the eigenvalue of Jacobian matrix. So you can get critical points from it. So you see that another critical point here, and I get Lyapunov exponent equals to 0. Another point somewhere here, which corresponds to bifurcation here. And now look here, we get Lyapunov exponent greater than 0, and this is the chaotic regime. And then here we have Lyapunov exponent less than 0, so this is this window of stability. So this is also this Lyapunov exponent is an important tool for capturing chaos, detecting chaos. So let's look through some of the examples. Let's actually compute this and see how pretty easy it is. So this, let's do the exercise 9.1. We wanted to generate bifurcation diagrams and compute the Lyapunov exponent for these maps. Okay, so I already set up the Mathematica notebook for this. So yeah, so this is the different f's that we want to analyze. Let's first let's first simulate, do a single simulation to test our code, right? And we will look at the logistic map. So f equals to rx times 1 minus x. And we'll choose some values of x, say 0.1, and initial value of x, 0.1, and initial value of r to 2. So this, then we'll do our usual simulation loop, right, and record our results. We'll do 100 steps. Okay. Then do the time series plot. So did it work? I think it doesn't work. Oh yeah, because I did not initialize my function. Okay, here we go. This is our usual logistic map. We can also do the cobweb plot. So I wrote a little module here for generated cobwebs. Okay. So now let's construct the bifurcation diagram and evaluate Lyapunov exponent. So let's have a look at the dissect sort of this code. So first we want to create generate a table of R values. So this is, yeah, so we want to evaluate the trajectory of a system for each value of R. Okay. So this first loop we vary W is over the values of R. Okay, so we initialize the system at 0.1. Select the R value from the list of R values. Then the first thing is to we simulate the dynamics for 100 steps, but we do not record the results. So this is just to settle our system into an equilibrium. And the next step will capture the points that the system is visiting at the attractor, at the equilibrium or attractor state. Okay, so it's just the usual update. So I record my results, but I also record this log of absolute value of df ry, the derivative of f with respect to x at the current x. So I do the derivative with respect to y, and then I substitute y to x. Yeah. So this will be used to get the Lyapunov exponent. So in the end, I have to take the average of that. So the Lyapunov exponent is the average of this quantity. Okay. So this is basically the code for computing this. So let's look how the diagram looks. So, yeah, so this is my bifurcation diagram. This is my Lyapunov exponent. Yeah, and then you can see that the location of bifurcations are consistent between the two. Yeah, by the way, you can actually analytically find the location of a first period Dublin bifurcation by looking at the eigenvalues of the Jacobian, but you can only obtain the analytically eigenvalue of the first, or you can only obtain analytically the location of the first period Dublin bifurcation. To obtain the analytically the location of the second the next period Dublin bifurcations, you have to use some other tricks, but let's not go into that. Okay, so let's repeat the whole calculation, but with different function f. So let's put f to, so what this map, x cubed minus r times x. Yep, this one. Okay, and let's go down here. Okay, so this, let's change the plot range. So yeah, here we, in this case, our map is defined for r between 0 and 3, and yeah, it looks like this. So actually x can take negative values in this case. We do not completely capture the whole diagram, so if we started with x in minus. Okay, the mathematics is sort of slow. Okay, let's minus here. So now we should get like additional branches, right? Yeah, you see, you could, to complete the diagram, you have to start with two different initial conditions, one positive, one negative. Okay, so this is the cubic map. You also see that you get this cascade of period doubling bifurcations. Next, let's look at this one, the sign map. Okay. Yeah. So now actually we can continue. Let's allow RP go up to 10. Still calculating. Okay, it's taking too long. But let's see how much data we got. Okay, so yeah, okay, here we go. So you get a different structure here a little bit. So it's also noted you also have period doubling cascades, and then region of stability and so on, and it's going to repeat and repeat. Here we go. Okay, and a final example is a little bit different. So okay, so f equals fractional part of 2xn. So it's actually the sawtooth map, this one. So this one's a bit different. You don't have any R parameters here. And if you select, let's see what's happening. So this is not really a chaotic, right? This is not chaotic. This is a periodic solution. But if I set x to an irrational number, let's say pi over 4, then this becomes a chaotic system. So it's quite interesting. So if your initial state is irrational, then this is a chaotic map. Whereas if it's a rational number, it's not chaotic. As an example, you can try looking at this the bifurcation diagram. Try to determine bifurcation diagram and Lebono exponent for the following discrete map as an exercise. And also, if you like, you can have a go at finding analytically the location of the period doubling bifurcations. And if you get stuck, you can refer to the Hiroki Sayama chapter. I think it's chapter 8 or 9, which describes how to do this. Okay, so I think that's so. Yeah, by the way, there are lots of interesting discrete chaotic maps. So if you have a look at Wikipedia, you have a huge number. So, I mean, here there's just a list which lists actually both discrete and continuous, but you can just if you're interested in chaos, you can try simulating many different chaotic maps. Okay, so that's for discrete dynamical system, and the next part we will move to an example of a continuous dynamical chaotic dynamical system.